let's talk about one of my favorite concepts in statistics. Welcome to this quick hits video. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. This video will cover a bit of introductory statistics that can catch people unawares, Bayes' theorem. Let's quickly go to the classroom and I'll introduce the topic. To prime the pump on this discussion, let's start with a common hypothetical scenario. Alien abductions are a danger that can affect any of us at any time, but we have a way to test for your likelihood of alien abduction. All you have to do is stick your hand into the box of pain for a little bit, and we'll know if the aliens will want you. Granted, our test isn't perfect. No test is, after all. About 5% of the time, we make a mistake and think you'll be abducted by aliens when you're actually going to be just fine. But hey, we get it right quite often. Now, we know from empirical research that 1 in 100,000 people will get abducted by aliens at some point in their lives. The question is as follows. Suppose you came down to our testing supercenter and stuck your hand into the official alien abduction box of pain. The test comes back positive that you're ripe for alien pickings. With our 5% false positive rate, what then is the probability that you're getting a free ride on a UFO? If you answer 95% to that question, stick around because this is going to be a helpful video for you. Bayes' theorem is named after Thomas Bayes, an English Presbyterian minister and statistician who lived during the 18th century. And in true Bayesian fashion, the one picture people believe could be Thomas Bayes quite possibly isn't. There's a probability that this image is of Thomas Bayes, but we aren't going to try to calculate that today. Instead, let's dig into the common formulation of Bayes' theorem. At its core, you'll see Bayes' theorem in this very common format, using A and B as the variable descriptors. I actually prefer the version that you see in the Stanford Encyclopedia of Philosophy using H and E. Conceptually, they're the same. After all, what you name the variable doesn't change the underlying calculations. But it turns out that H and E hold a bit more meaning for hypothesis and evidence. Now, for this video, I will use the common forms of A and B, and I will focus on the event explanation form of Bayes' theorem, so we won't get into hypothesis and explanation, but I will just say for the record that I do kind of prefer that explanation and notion. If we look at the formula, we have that P of A bar B is equal to the quantity of P of B bar A multiplied by P of A, all divided by P of B. If you're not at all familiar with statistics, let me describe this for you in layman's terms. If you are very familiar with statistics, forgive in advance my oversimplification of the description. Or write a 3,000-word missive in the comments. Your call. In this formula, A and B are events. They are things that we can measure or observe. P of something represents the probability of that thing occurring. For example, P of A represents the probability or likelihood that event A will be true or will happen. P of A needs to fit into the range from 0 to 1, where 1 means that event A will always happen, and 0 means that event A will never happen. P of B, similarly, needs to fit into this range, except that P of B must be above 0. If P of B is 0, well, we have a divide by 0 problem, and then the aliens get away with their abductions because our high-pursuit mathematical interceptor vehicle crashes into a wall. And we don't want that to happen. Now, on the left-hand side, we have a formula that includes a vertical bar. We read that bar in English as the word given. In other words, it's P of A given B. This is the probability that event A occurs given that event B has occurred. Similarly, P of B given A is the probability that event B occurs given that event A has occurred. You'll often hear people describe this as conditional probability, the probability that event A occurs conditional upon event B. As a quick aside, the problem with describing these two parts of the formula as conditional probabilities is that all probabilities are conditional. There is no such thing as a non-conditional probability, and even in this formula, we're secretly hiding away plenty of conditions around the existence of aliens, the existence of humans, the existence of our test, and much more. Because I'm trying to keep this at a most introductory level, I won't dig any deeper into this aside, but please take into consideration in your 3,000 word comment that I am aware of this. Okay, back to the formula. Now, there are a few terms that you'll hear Bayesians throw around a lot. Let's briefly explain them. First, we have the term prior probability. We represent this as P of A, and it represents the likelihood of event A happening, given all of those other conditions we're currently sweeping under the rug for simplicity, prior to our new information about event B. In my example from before, this is the probability of an alien abduction. P of B represents the marginal probability, or the new evidence we introduce into this discussion. This is the probability that our test of alien abductability will return true. Then P of B given A represents the likelihood of A occurring, assuming some fixed B. In other words, this is the likelihood, given that aliens actually abduct a person, that our test indicated the person would be a risk candidate for alien abduction. Finally, P of A given B is our posterior probability, or posterior probability, depending on how you want to pronounce it. And this is the thing that we really want to know. In other words, we start with a prior probability of alien abduction. Then, armed with the new information we received from a test of alien abductability, we have a new probability that aliens will engage the tractor beam on a particular person. Now, I'm not going to dig into the proof of Bayes' theorem, though I will note that Wikipedia has a pretty neat visual proof of it. You can review that on your own time, or if you want me to go through the proof, leave a comment below and maybe I'll put on my professor hat and provide a detailed explanation. But again, for the sake of using Bayes' theorem, I think it's okay for us to understand how to use the formula rather than deriving the formula in this video. Now that we've described the formula, let's see how all of the pieces fit together. Returning to our totally realistic scenario, we know that 1 in 100,000 people will be on the wrong end of an alien abduction. We know that our alien abduction likelihood test has a 5% false positive rate. But the question is, where do all of these fit and how do we get our final answer? Well, 1 in 100,000 is also known as the prior probability. This is the probability of an event occurring, given whatever circumstances exist, but before we learn additional information. We know that this is P of A in the formula. 5% is the false positive rate, but this does not imply that the true positive rate is 95%. To understand why, let me show you a box. But not the box of pain. That's a proprietary medical device, and I'm not allowed to show it on camera. Now, I have a two-dimensional confusion matrix here. This is a simple example of a confusion matrix, so we can speak in terms of true and false, positive and negative results. In the top left corner, we have 98 true positives. In other words, the person took the test indicated alien abduction, and that person got abducted by aliens. Hooray! We had 2 people with false negatives. They took the test, we thought they were not going to be at risk, but it turns out they actually were at high risk of alien abduction. Meanwhile, on the bottom side, we have 5 false positives. We told 5 people that they were at high risk of alien abduction, but it turns out that they really weren't. Finally, we have 95 people who took the test, did not come out as high risk, and actually weren't at high risk. This information is critical because it gives us everything we need. So let's squirrel this confusion matrix away on the screen for a little bit and come back to it soon. Now, I'd like to relabel this generic version of Bayes' theorem with some slightly more helpful names. Instead of using A and B, I'm going to use the terms abduction and positive, respectively, where positive means that the test returns a result that you are at risk for alien abduction, and abduction means you actually get abducted by aliens. Armed with this information, we can resolve the question. Let's start by replacing P of abduction with our value of 1 in 100,000. Next, we need to solve 2 more bits to get to our final answer. First up is the probability, given that a person is an alien abductee, that we got it right. The way to calculate this is to take the number of true positives and divide it by the sum of true positives and false negatives. That is 98 true positives over 100 positive results. Thus, our value here is 0.98. The bottom is a little more complex because we need to calculate how often we should return a positive result. We need to break out P of positive into two separate categories. First up is our calculation of true positives multiplied by the probability of abduction. The other side of the coin is the probability that we estimate a person is at high risk, but the person is actually at low risk, multiplied by the probability of being a low risk for abduction. Now, we already know the answer to the first part. It's exactly the same as the numerator. So let's replace those numbers right now. As for the second half of the equation, the probability of a positive result given low risk for abduction is also known as the false positive rate, which we know is 5% based on the information we received in the initial problem description. And the probability a person is not going to get abducted is 1 minus the probability of abduction, so we have 5 nines after the decimal point. At this point, it is a fairly straightforward arithmetic calculation to get our result. That's right, a positive test here makes it so that your probability of getting abducted by aliens goes from 1 in 100,000 all the way up to 19.6 in 100,000. To put it as clearly as I can, instead of a 95% probability, given a positive test, that aliens will abduct you, you have a 1 in 5,000 chance of getting abducted by aliens, given that you tested positive. You have a 99.98% chance of not being abducted by aliens, even after testing positive for alien abductability. To provide just a little more context here in what may seem like a counterintuitive result, the reason our test moves the needle so little relies on two factors. The first is the extremely low likelihood of the event occurring. 1 in 100,000 means that, of course, 99.999% of the time, that thing will not happen. Then we multiply this by the false positive ratio. 5% may sound like a good number at first blush, and in fairness, if alien abductions happened 50 or 60% of the time, the story is quite different and our test becomes more meaningful. In fact, let's change this value and see how the numbers change. Here's what the formula looked like before we started filling in the numbers. Now, instead of 1 in 100,000 people abducted by aliens, let's say that 2 out of every 3 people get abducted. Our probability of a positive result given an alien abduction remains 0.98. On the bottom row, we replace the first half of the formula with what we knew before. And for the other half, we know that the false positive ratio is 5% and 1 out of 3 people do not get abducted. Now, prior to the test, we had an expected probability of alien abduction at 2/3. After a positive result, we can see a 97.5% chance of aliens abducting our poor test taker. That's the real intuition we should draw from this. How much the positive test should affect our expectations of an event taking place really depends on the false positive rate and especially the original likelihood of the event occurring. The less likely our event is to occur, the lower our false positive rate needs to be if we want to move the needle. I hope you enjoyed this quick hits video. Bayes' theorem is something we go over in pretty much every statistics course, but in my experience, so much of that explanation was of the watch me derive a formula and then you mindlessly plug values to get an answer sort. What I wanted to do here was to give you a better understanding of how it works, especially because I think it helps us make better decisions and learn how not to overreact to some piece of information. Even if you don't have hard numbers for each of these values, rough estimates and knowledge of the formula will lead to a better decision-making process. We'll have links and show notes in the description below, and until we see each other in the next video, take care.